Hello. Today we're going to be talking about something called implicit differentiation. I think this will be pretty short. I don't have anything deep or original to say about this. What is implicit differentiation? Okay, well, we have been differentiating every single possible function over the past 6 weeks, and we finished. We now know how to differentiate every single function that we encountered ever in pre-calc. And this you could think of as kind of an extension to that subject. What is differentiation? Well, one interpretation, a geometric interpretation, is that we are finding the slope of the tangent line to a curve in order that we may calculate the instantaneous velocity. And so now let's find the slopes of tangent lines to curves, which are not necessarily functions. Alright, and consider the following simple curve. The curve x squared plus y squared equals 25. Okay, so this is something you encounter in Algebra 1. This is just the equation of a circle, centered at the origin with radius 5. That's because this is expressing a Pythagorean relationship, and so, yeah, basically any time you have two legs of length x and y and a hypotenuse of length 5, then that point will satisfy this equation. And so what you end up with is all of the points. Yeah, well, let's draw it. Cha, 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 cha. All right, so maybe it doesn't make any sense to reteach the equation of a circle, so I guess I won't. But pretty bad circle too. So if that's 5, 0, then this circle has radius 5. And any point whatsoever, x, y, on this circle will satisfy this equation because of the Pythagorean theorem. So, great. Let's take a particular point, say 4, 3, on this circle. Of course, it satisfies this equation. And it's also true, helps to think visually, that this is over 4 and up 3. So 4, 3. And then this hypotenuse has length 5, of course, because it's a circle of radius 5. It's 3, 4, 5 triangle. All right. Now I have a question, and the question is, what is the slope of the tangent line to this curve? So I make a curve, or I make a tangent line to the circle at the point 4, 3, and you might be having some kind of weird feeling because we've been calculating slopes of tangent lines to curves for 6 weeks, but actually this is one that you already knew about. This is a particular curve that you already, before this class started, knew how to find the slope of the tangent line to. In fact, there was a homework problem like on the first week of the semester that asked you to find the slope of the tangent line to a circle. Circles are special objects, and there's a thing that you learn in geometry, perhaps you even prove it, called the tangent theorem. The tangent theorem says that a tangent line to a circle is perpendicular to the radius drawn to the point of tangency. In other words, this purple radius is perpendicular to this red radius. So, then I can just use Algebra 1 techniques, so to speak. What is the slope of this purple line? Well, we just go up 3 over 4, so the slope of this line is 3/4. And if this red line is perpendicular to it, then by another Algebra 1 theorem that you may or may not understand, the slope of this line and the slope of the purple line are negative reciprocals, so-called negative reciprocals, and so this line will have slope negative 4/3. Okay, great. That looks about right, and kind of problem solved. So in other words, you already knew how to find the slopes of tangent lines to some curves before you even did calculus. And maybe this is a good time to. I changed my mind. I do have something deep to say about this subject. I guess. Okay, so this is what's true for that particular point 4, 3. Maybe we can extend this now to a general discussion of the slope of the tangent line to any point whatsoever. And let's do it. I now basically same picture, but now instead of calling this point 4, 3, let's call it x, y. And x, y. And well, it's the same thing. I go over x, up y, cha-cha-cha, over x, up y, and so there's a tangent line here, and well, what's the slope of the tangent line? The slope of the tangent line is going to be, or the tangent line itself is going to be perpendicular to this, and what is this purple line? Well, it has a slope equal to y over x, and therefore the slope of this red line is going to be negative x over y. And so I think what we have just proved is, in general, an equation for the slope of the tangent line to a circle. And that formula has kind of two inputs to it, you know, the x-coordinate and the y-coordinate of the point on that circle. Okay, and how is this related to differentiation, you might say? Well, it is, right? Because, maybe now just erasing this a little bit for clarity, of course, what are we really sort of saying when we're saying that this tangent line has a certain slope? Well, to connect this back to the way we've been treating tangent lines for the past 6 weeks, what that means is if you sort of zoom in and zoom in and zoom in on this curve, then this curve is pretty much like the tangent line. And so what we're really saying is that this curve has the property that at the point x comma y, if you go down some tiny bit and over some other tiny bit, and here I'll be vague about whether that is touching the tangent line or the function itself, or the curve itself, because they're the same thing when you zoom in, that this is delta y and this is delta x. In other words, what we are really saying is when I say that the slope of this tangent line is negative x over y, I really mean that the slope of this line, delta y over the change in y over the change in x, for this tangent line is negative x over y. And in other words, what I'm really saying, in some sense, is that the infinitesimal change in y over the infinitesimal change in x is negative x over y. And so, in other words, dy dx, if you're very comfortable with this sort of geometric interpretation of dy dx, then what you want to say about this line is that the slope of this line is just dy dx. The infinitesimal change in y over the infinitesimal change in x for 2 points that are very, very close together on this curve, which is kind of saying the same thing as the slope of the tangent. Okay, and what does that have to do with like kind of velocity or anything? Well, it does have a lot to do with velocity. In fact, something I think I never said this year, but is in my sort of plan of things to say every year. You know, one way to think about the tangent line is to bring it all back to circles. So when you are taking physics for the first time, you learn about this thing called centripetal motion. What's centripetal motion? Well, you take some sort of object on a string and you swing it around. And you sort of swing it around and swing it around and swing it around. Okay, so here I am, swinging this object around on a string, and it's moving in a circle, and what is something that takes some investigation to tease apart is that the force on this object is actually pulling inwards. What makes the object move in a circle is that I'm exerting a force on it at every moment, pulling it towards the center. And okay, what you also learn when you first learn this topic in physics is if you have some object moving around and around in a circle, then if you let go of that object, what will happen to it is that it will go sort of flying off in a straight line. And it will go flying off in a line which is tangent to the circle. And okay, if you do this in a situation in which there's no gravity, that sort of simplifies things a little bit, and you have the only force acting on the object is the so-called centripetal force, the force that's pulling this object towards the center. Then, if that's the force on the object, then this, we say, is the velocity vector. I think that was even taught to you exactly like this back in freshman physics. In other words, the velocity vector is always perpendicular to the force vector. Okay, and if you think about what that's really saying that at every single moment, as the object is spinning around and around in a circle, at every single moment, the instantaneous velocity at that moment is actually perpendicular to the circle. And you see that by letting go, because one of the basic Newtonian principles of physics is that that an object not under any kind of force will continue moving kind of in a straight line forever. In other words, when you let go of the object that you're spinning, now you've removed that force on the object, and if we're pretending that there's no gravity, then there are now no forces acting on that object. And when there are no forces acting on an object, it will just keep moving forever in a straight line. Which is to say that the path that this object takes when you let go captures sort of what the velocity vector was at that moment. The velocity vector at that moment is the instantaneous rate at which that object was moving. But since we're doing it since we're moving in 2 dimensions, it's actually capturing the direction also. Okay, this is kind of like a long-winded and rambly way of saying that when you let go of something, then it continues doing what it was doing at that moment. It's a way of kind of locking in the velocity. And something we didn't do this year was to connect this back to the basic concept of a tangent line. Kind of crazy that I'm doing this on the video that maybe no one will even watch. But if you give me some function, and we spent a long time talking about how and why the slope of the tangent line to the curve is the instantaneous velocity. But I think what never came up, and I never made it come up, is like what even sort of is the tangent line? And the answer is you can think of the tangent line as locking in the instantaneous velocity at that moment. That is to say, the slope of the tangent line is the derivative of the function at A. And okay, if this is a position versus time curve, then it means that the slope of that line is the instantaneous velocity. Okay, but what is the tangent line? You can think of the tangent line itself as being kind of an alternative position curve. It's the position curve in the hypothetical situation in which at time A you let go. That is to say, we have some position versus time curve. The velocity is changing at every moment, as can be seen by looking at the slopes of the tangents. So if the velocity is changing, what's changing the velocity? Well, it means that if the velocity is changing, it means there's some acceleration. Because that's what changes velocity. If there's some acceleration, it means there's some sort of force. In other words, there must be some force acting on this object, causing it to accelerate, causing its velocity to be continuously changing. Well, if at time A, you simply let go of the string and remove the force, then the object is no longer accelerating, then the velocity is no longer changing, then the velocity from this point on will be the velocity that the object had at that moment. Then you can think of, and now I'll erase, to make the story make sense, I'll erase the left part of the line. You can think of, from time A on, you can think of the purple tangent as being the path that the object would take if at time A you stopped exerting a force on the object, stopped accelerating it, and therefore locked in the velocity. So okay, that's a kind of a way of sort of saying like, what is a tangent line? One answer is, a tangent line is what the object would continue doing if the velocity continued to be exactly what the velocity was, the instantaneous velocity was at time A. Okay, and so the circle provides a kind of an understanding of this because you sort of already knew in some sense, if you've taken physics, that the velocity vector was perpendicular to the force vector. You can sort of think of the tangent line to a curve as being the path that the object takes when you let go, something you already knew. Okay, what the heck are we doing? Well, we're going around and around in a circle talking about derivatives. I think what's interesting is that, so and maybe now I'll write like calculus, because this entire problem over here, though I'm using the language of calculus, I am not actually using any calculus because I didn't have to. That's because circles are so easy and simple. They're the only simple curve that we can calculate the tangent line to, sort of without doing any kind of algebraic calculations, we can just use geometry theorems. That's what we've done. Okay, so now let's sort of redo the problem, but now with the full power of calculus, and we should sort of get the same answer. Now when I say redo the problem, I mean now not using any kind of a deep geometric understanding, but just taking the equation x squared plus y squared equals 25. Let's take the derivative, and I'll maybe even write over here, take the derivative, because that's kind of a lazy thing to say, and there's the potential for confusion there. What does that mean, to take the derivative or to differentiate? Well, we're going to differentiate both sides with respect to x. And I had students, especially like 10 years ago when I used to teach this class differently, without all of this kind of geometric intuition. Some people are sort of overwhelmed by this step that we're about to take, because we have been sort of extremely careful for the past 5 weeks to, we defined limits very, very precisely. We have a very, very precise understanding of what a limit is. We have defined derivatives as limits, and so we know exactly, if you want to, you can take things all the way back to the definition, and every time that we differentiate, we're calculating some kind of precise limit of some kind of function, and after doing this for over a month, now suddenly, seemingly, the class goes, let's not worry about all that kind of definition stuff. Let's just take the derivatives of things which are not functions. And of course, x squared plus y squared equals 25 is not a function. So I'll even just write that, this is not a function. And what we mean when we say that this is not a function, what we really mean is y is not a function of x. Or the other way around, but that's kind of what we mean. This is more just algebra 1. You can see that for the same x value, say 4, there are multiple points, there are multiple y value outputs, 4, 3, 4, -3. So this is not a function in the algebra 1 sense. But that doesn't mean that we should somehow exclude it from the sort of domain of curves that we can investigate. In fact, historically, Newton and Leibniz and the people who did calculus for the first 100 years after them, they had no such distinction. In fact, they immediately considered slopes of tangent lines to curves, because in fact they thought of geometry as just the study of curves. And this modern idea of a function for which a single input produces a precise and unique output, that came only much later. So they would have considered this to be a totally natural thing to do. Alright. So this is y is not a function of x, but the answer is who cares? What we're now going to do is we're just going to differentiate. So you sprinkle some of your magic calculus pixie dust on both sides of this equation, and what I mean by that is we're going to take the derivative of both sides. Okay, and we're going to take the derivative of both sides with respect to x, so to say. Okay, and so really what we're doing is we're taking two things which are equal, and we're saying, okay, well, if they're equal, then the rate at which they are changing with respect to x must also be equal. Okay, okay, let's just kind of do it. Here, for the first time ever, we will be careful and stuff, and this is a sum of two things, so I'm going to write it as the derivative with respect to x of x squared plus the derivative with respect to x of y squared. And of course the derivative of 25 is just 0 because that's just a constant. Okay, so great. What is the derivative of x squared? Of course that's just 2x, so there's nothing to talk about there. But this is kind of like the moment of truth or something. What is the derivative with respect to x of y squared? You might be tempted to say, oh, that's just 2y, but of course that is not quite right. What is true is that the derivative with respect to y of y squared is 2y. But we are not differentiating with respect to y, we're differentiating with respect to x. And so we've been doing this for about a week now, so hopefully this is now becoming a little bit more comfortable to you, but you should recognize this as a chain rule situation. It's just like when we differentiated in this class, this came first, when we took the derivative of ln y, and I encourage you to see that the chain rule was necessary here, because this is actually a composite function, the inner function being y, the outer function being ln, and so we got 1 over y back inside dy dx. It's the same thing here. The outer function, the inner function is y, and the outer function is y squared. And so the derivative of y squared is, well, the derivative of something squared is 2 something back inside for the derivative of the something. Okay, if you're just okay with that, then great. If you're not okay with that, then you can just sort of cycle through the various deep understandings of the chain rule that you have until you talk yourself into this being like totally correct. Because, after all, there's this thing y. Now, what is y? What does make this kind of 5% different than anything we've done so far is that I referred to y as a function of x, but y is not really a function of x. In fact, I just wrote on the board, y is not a function of x. So what is y actually? Well, y is something that depends on x. I think that's the simplest way of putting it. And what people say in this situation is that though y is not a function of x, what people say is that the equation x squared plus y squared equals 25 implicitly defines y as a function of x, or something like that. Okay, so it's not a maybe I shouldn't even use the word function. Implicitly defines y in terms of x. In terms of x. In other words, though y is not a function of x, it's not the case that you plug in a particular x and a particular y comes out. There is a relationship between x and y, and the relationship between x and y is not being given in terms of a explicit relationship. What you might consider, I'm just filling up this board with little scribbles, what you might consider an explicit definition of y in terms of x would be one that's kind of functional. So, I don't know, if y equals x squared sort of explicitly defines y in terms of x. Okay, no one ever goes into this detail, but this is to say that by giving you the formula for y in terms of x, I've told you exactly how to compute y. You give me an x, I give you y. In other words, that's just what we think of as the modern function definition. You can think of this as an explicit definition of y. If you know what these words explicit and implicit mean, then this is kind of an example of this. Whereas here, I'm not quite telling you how to get a y, but there is a relationship between x and y. That relationship is implicit in this. That definition is implicit in this relationship. Okay, so that's why this is called implicit differentiation. It's not really like important that you know that, but anyway. And then, of course, okay, so if you're just okay with that, right, that x and y have a certain relationship. So what is y? Y is something that depends on x. And therefore, I am now differentiating the square of that thing that depends on x. And so what is the rate of change of y squared for a small change in x? This is the good way of thinking about the chain rule. Well, if you change x by a tiny, tiny bit, we now ask, at what rate does y squared change? Answer, dy dx explains how fast y changes for a small change in x. So that rate at which y is changing needs to be multiplied by the rate at which the outer function is changing. And so, okay, there it is. It is in some sense just the chain rule, and it's not different from this thing that we were doing last week. It's only different in that now you can't point to y and say exactly what it is anymore, but otherwise the logic is exactly the same. Okay, once you're sort of over that psychological hurdle, most people just learn it and just don't worry about it too much, and don't even think about it. Of course, we can divide by 2, and we get x plus y times dy dx equals 0, and I can even just do some algebra 1 now. So I get y dy dx equals negative x, and finally I have a formula. The formula is that dy dx is negative x over y. And so what I've now done is, without any geometry, just using calculus, so to speak, and differentiation formulas and the chain rule, I have proved to you that the slope of this curve, dy dx, the change in y with respect to the change in x, which you can think of as, which you can interpret geometrically as the slope of the tangent line, is negative x over y. And of course, this is exactly the formula that we got over here when we did it just using geometry. Okay, and I just have one final thing to say. What is this? You should think of this as a formula. It's a formula which takes as an input a point x comma y on the curve. So let's just do another one. What is dy dx at, say, well, pick another nice point on the curve. How about negative 3 comma 4? Okay, so if you go over here to negative 3 comma 4, probably purple is probably barely showing up. But of course, that is a point on the curve. And if you draw the tangent line to the curve there, and now we can calculate the slope of it. How? So the notation that people write here is at the point, dy dx at the point, negative 3 comma 4. Well, I just plug into this formula. I plug in negative 3 for x, and so I get 3 on the top, and I plug in y on the bottom, and so I get 3/4. And so my formula tells me that the slope of this line is 3/4. Okay, that's basically it. Let's do like one example, and then we'll stop, because that's all I did in regular class. There's this worksheet called Implicit Differentiation, and there's this curve. Some kid once jokingly called it Shrek's ear. It looks a lot like Shrek's ear. So you're going to download this, and we're going to do this one problem, which takes 5 minutes, and then that's probably all the education you need on this topic. It's actually probably way more than you needed or wanted. All right. Okay, so here is an equation, and when you download this worksheet, you might be sort of blown away by the sudden kind of complexity. That's how math works. Every time you think that you are becoming an expert on a topic, someone cracks the door open and you see that there's just an entire gigantic world of math out there that's like way harder than anything you've ever considered, and you don't know anything about it. That's how you should feel about suddenly being presented with the curve x cubed minus xy plus y squared equals 4. It's bewildering. What is this curve? I thought I knew how to graph. I thought I knew all the functions. I thought I knew how to graph all the functions. Suddenly, I'm being given some crazy thing in which I have x's and y's being multiplied by each other. So, yeah, that's right. This is called a cubic curve. It's a cubic curve because, well, it's a two-dimensional curve defined with, x's and y's. And it's a polynomial, but it's a cubic polynomial because the highest power of x or y or their product is 3. And this was a very important topic, and the people who invented calculus were investigating these cubic curves, and in fact one of the most impressive things that Newton and Leibniz could do, that no one else could do, was to perform these kinds of analyses of these cubic curves that were important sort of for other reasons. Okay, so I'm going to definitely pass this out in class because it's very hard to draw these. And so my drawing is going to be kind of bad because never have done this before. Actually, that's not so terrible. Okay, so this is the cubic curve, x cubed minus xy plus y squared equals 4. And now we're going to do something that we never could have done in pre-calculus, which is to analyze this curve. And one of the things that will tell you what this curve looks like is if you knew what the slopes of all the tangent lines were. And it turns out that this is just easy. So in other words, what we do is we take this curve. The goal is to just find dy dx. What does that mean? Depends on how you look at it. One way of thinking of this question is we're just finding a formula for the slope of the tangent line to the curve everywhere. That's how normal people teach it. You can also, if you want to turn this into a physics problem, you could say you have some object moving along this curve, and the question is, what is the instantaneous velocity at any given moment? The instantaneous velocity will be the slope of the tangent line to this curve. Okay, let's go. What do? We just take the derivative of both sides. So we take the derivative of this and the derivative of this. And if these these two things are the same, and so their derivatives are the same. So okay, let's go one more time, just being kind of careful. Normally I would not insert this step. But the derivative of 4 is just 0, and the derivative of the left-hand side is the sum of 3 terms, so I'm going to split that up into 3 separate derivatives. Okay, let's go. If I'm differentiating x cubed with respect to x, then that's just 3x squared. But now we have to be kind of careful. I'm differentiating the derivative of xy. So what is the derivative of xy? Well, what is y? Okay, answer, y is something that depends on x. And here, it would be very difficult, bordering on impossible, for me to write the equation of y. If you demanded that I give you the formula for y, I would just cry and change the subject, because I don't want to solve for y, and in fact maybe I even can't. But there is a relationship between x and y, and this equation defines that relationship, okay? So what is y? Y is something that depends on x. Though it's not possible to give an explicit definition of y, I have given an implicit definition of y by giving you the equation that relates x and y. Alright, repeating myself. Therefore, y you should think of as some kind of complicated thing involving a bunch of x's. And therefore, people who are observant or lucky or whatever recognize that I have to use the product rule here. I'm really multiplying two things. I'm multiplying x and some complicated thing that depends on x. Uh-oh, my children are coming. So we now do the product rule. The product rule says that if you're taking the derivative of the product of two things, it's the derivative of the first one, which is 1, times the second, plus the first, x, times the derivative of the second. And the derivative of y is dy dx. Children, can you go ahead and just make it a video? Okay, good. Maybe we should just finish this off. What is the derivative of y squared? The derivative of y squared is, okay, well this is something we basically already did. I'm going, shh, no opening the gate. I'm taking the derivative with respect to x, and so the derivative of something squared is 2 something.
Open the gate, Papa.
No, I'm not opening the gate. Is the derivative of something squared is 2 something back inside for the derivative of the something. So now I have this complicated expression, but hopefully you now see that it's just a bunch of algebra, right? You get minus y minus x dy dx plus 2y dy dx, and now you just interpret dy dx algebraically. No, Ada, go away. Okay. No.
Yes.
I'm making a video.
But I need to draw. I want to draw.
No, you can't draw.
When you're done.
Yes, when I'm done. So I moved these two terms over to the other side because they don't have x. Wait, shh. Because they don't have any dy dx in them. I factored out dy dx and now I divide them.
If I want to draw, I have to go inside here.
I know, but I don't want you to draw, so that's why I'm not letting you in.
I want to draw.
Oh, I want you to not draw. Okay, good. So what is this? This is a formula, and this formula tells you, for any point whatsoever, the slope of the tangent line to the curve. And just to see this formula in action, consider a particular point, like this one here. Okay, from your picture, it certainly looks like this curve goes through the point 0, 2. Of course, we can prove that, like just set x equal to 0. If you set x equal to 0 in this equation, then you get y squared equals 4, and so y is plus or minus 2. In other words, there is a point 0, 2, and there is also a point 0, -2 on this curve, which is of course just what it looks like. What's the slope of that red line? Well, you just take your formula, dy dx, and you ask your formula, so to speak, what is the slope at the point 0, 2? You plug in 0 for x, and you plug in 2 for y, and you get 2 over 2 times 2. And so the slope of the tangent line to this curve is 1/2, and it certainly looks like 1/2. Okay, we can do one more because there's another point here. What is the slope of the tangent line here? Again, we just do it. We take this formula dy dx and we plug in a particular ordered pair. That ordered pair is 0, -2, and what do we get? We get -2 over 2 times -2, so it's also 1/2. So it's very plausible, and in fact it's true, but it looks like it's true on the picture that the slope of this tangent line is 1/2. So, okay, cool. The tangent lines to sort of Shrek's ear are both 1/2. All right, good. That was your lesson on implicit differentiation. Goodbye, kids. Say bye.